Welcome back. Today I will talk about duration, and I want to derive duration using calculus. After this initial exercise, we will talk about modified duration, which refers to percentage price changes. And finally, we think about duration in a bond portfolio. Let me start with what we already know. We can describe the price of a fixed income security based on deriving the future values of cash flows. Now let's see denote our coupon payments. We know that we can write the value of a bond as the coupon payment divided by R, which gives me a perpetuity, and then I do an adjustment for the fact that it's not a perpetuity because I only get this payment up to maturity at point in time capital T. So just write down this part of the valuation formula which we derived before. Again, of course, you might like to modify this for semi-annual payments, which of course means I have to adjust the coupon rates and I have to adjust the yields. I don't do this because mathematically it doesn't make any difference, it's just a different scaling. And here we add our principal amount, which I denote M, and then 1 divided by R, our discount rate, and power of T. The main point I want to stress here is that C in this case would be the coupon payment. Yeah? So C is actually the coupon rate times my par value. Yeah? It just simplifies the notation. On the slides I have done things a bit differently, but that is just a simpler way of combining it because it doesn't matter from a mathematical perspective. So when we talk about duration, what we actually talk about is we talk about what happens to the price if the interest rate or the yield here is changing. So basically we want to determine dP/dr. So we talk about a marginal change of the yield and assess the impact on price. So from a calculus perspective, we simply take the first derivative. Now when we just look at this equation, we have the first term, which is a product, so I just use the product rule and I just simply do it step by step. Let's do that. So we get here a minus C, it's just a constant, R to the power of 2, and the second term just stays. So this is 1 minus 1 plus R power of T. So that's the first part, and then I apply the same to the second part, and I do an addition here. So it's we add C divided by R, and then I consider the second part. I get T in front, and then 1 plus R T plus 1. And here, of course, we note the fact that this minus goes because we have minus 1 times minus 1, so that should be correct. And then we have the final term, which is our term with the principal amount. So here we get minus T M and then 1 plus R T plus 1. So looking at that, I think this looks reasonably solid. So we have derived our first derivative. Now we could start collecting terms and doing a bit of a tidy up. That might be useful. Let's do that. Little bit of a tidy up here. So we do again dP/dr. The first term is quite acceptable actually, so it's minus your coupon payment and then the yield power of 2 and this component here. And then we have the second term and the third term, which we could combine. Again, of course, that's entirely up to you whether you want to do this. It would be, I think, quite useful to do it. So let me just write this down. We can do here a plus, and then we do our maturity and put this out. So it's CR minus M, and we divide here by 1 plus R to the power of capital T1. So that should be our duration. Now when we look at these terms, we could argue the following. So obviously this term here, this term looks positive, yeah, for reasonable values, I would argue. And so the first part here is definitely a negative. The second part, well, it depends on the amount of coupon payments, yeah, but also likely to be a negative part, again, for reasonable values. But again, of course, it depends indeed on how far we go with our yield. So that would be the duration derived. I just want to look now at a special case. And the special case is the zero coupon bond. Yeah. So what if we look at a zero coupon bond? Yeah. Let me just consider this. So we have a zero coupon bond. The name already tells you that we basically have to set the coupon payments equal to 0. So we spoke about this already before. So this bond does not pay anything before maturity, and at maturity you just get a principal amount back. So actually everything is included in the final payment, to be precise. Good, so what can we say about the duration? So obviously if we just set c equal to 0 in the above equation, the first term drops, the second term simplifies to minus t m for the principal, and then 1 plus r to the power of t plus 1. Yeah, so that would be the duration for a zero coupon bond. Good. Let's have another little think about what we need to do if we talk about a modified duration. So in a modified duration, we just have to consider our reference point, basically. Yeah? So a modified duration, I might denote this as d, would refer to our initial measure, so dpdr as denoted above, and then we basically refer this to the bond price. Yeah, that's all we do, and that would give us a modified duration. Now it would be a nice exercise if you can try to add 2 more functions to our bond functions in the Python script, where we can calculate duration and modified duration. So just give that a try and see how it goes. Now I want to do one more thing in this exercise. I want to consider what happens to duration in a bond portfolio. Yeah. So in a bond portfolio you have several bonds, and we could just now start a bit of notation here, just to make sure we understand what we are talking about. So we have the price of bonds P I, and so that would be the bond price. These bonds might be plentiful, so we could consider, so this is basically bond price of security I, and then we will have here I running from 1 to up to capital N. Yeah? So we have N securities, and we have some weights as well. Yeah? So portfolio weights, I just use omega here, omega I. So this is basically my portfolio weight. Yeah? And then of course we could impose certain restrictions if we want to. So for instance, do I have to be fully invested or not? But let me just, without much loss of generality, assume that if I sum over all these omega i's, this is equal to 1. So this means basically you're fully invested in a bond portfolio. Now, when we think about the value of the portfolio, well, we could easily, of course, derive that based on these assumptions. So we can just write down here a portfolio value, so which is maybe denoted P, and I now use maybe omega. Let's do this because PP is a bit silly. So this would be my portfolio value, which would be simply the weighted average of my individual bonds. So it's simply something like this, PI. That would be the portfolio value. Now, if you then think about a portfolio duration, well, what happens? So what you do is you simply do a derivative of your portfolio value with respect to a yield R. Now, this yield R does not have a direct impact on your weights, so from a summation perspective, it just goes through to the next term, and you would end up with this equation. So basically, this equation tells you that the duration of a portfolio is simply the weighted sum of durations. So that's all you need to know. Good, I'll see you in the next one.